Okay, we are going to talk about the factors affecting the period of a mass oscillating on a vertical spring. Okay, so we're going to have here a mass on this vertical spring. And you might ask, hey, why are we going to use a vertical spring? Because we considered a mass on a frictionless horizontal surface, right? We had a mass going back and forth, left and right. But I don't have a frictionless surface, okay? And this is actually going to provide a very good frictionless surface here. If I go like this, it bounces up and down, and that's going to go for a long time. So not much air resistance. The spring is going to slowly also warm up, and this oscillation is going to die down, but it works very well. So we're going to use a vertical spring, partly for that reason. But or mostly for that reason, but we do have to watch out about one thing. The spring will also need to stay straight while squishing. When we had a mass going back and forth, left and right, something like this, right? The spring squishes. Well, in real life, it's hard to get a spring to actually squish. So if you're going to take a look at our spring, we're going to need to make sure that the spring never gets up so high that it gets past this point. Because if the mass were to get up here and keep going, the spring doesn't really squish very nicely. It kind of bends and moves out of the way here. So maybe I should move this over here. So it bends. So we never want this mass to get too high, which means when we pull this down, we're going to make it oscillate. We don't want to pull down too far. Let's say this goes down, I don't know, people are getting about maybe a little less than, but roughly 4 centimeters that this goes down. If I pull it down, this 5 more centimeters, okay, what happens when it goes up? It can just come up and fly off the spring, because when the spring gets back to this point, the mass is still moving upward and the spring is supposed to squish, but it doesn't really squish. So we're going to need to make sure that our mass never gets this high, which means we'll have to worry about not making this amplitude too big. Okay, so our spring won't squish, so we need to make sure the spring never squishes. It won't squish nicely, so don't let it get past or back to its relaxed length. Okay, now what could affect the period? What could affect the period of oscillation of that spring? Like, what could I change in this setup that would change? So here's the period, right? So actually, I'm going to add another mass on there so it's not quite so fast. Probably a little easier, especially with Zoom. I'll make it go down just a touch. So, 0, 1, 2, 3, 4, 5, right? So a period would be from there to there, yeah? What could we change that would affect that period about the setup? So you can stop it for a moment, talk with your group. What would affect the period of the oscillation in that setup? Well, one thing, you can take out a piece of paper. Actually, I didn't say that. So take out a piece of paper. You can pause the video if you need to. You're going to write just this top part here. Factors affecting the period of a mass oscillating on a vertical spring. Okay. And then what could affect the period? Well, we could change this mass, right? We could make it a different mass. It doesn't matter whether it's made of brass or zinc or whatever, but change that mass. We could also change how far down we pull it, right? Maybe if we pull it down, this much, and then we pull it down farther, maybe that will affect the period. We could also change things about the spring. But if you think about it, the masses don't really know what the spring is like. It doesn't know how long the spring is, or how thick these coils are, or how far apart the coils are from coil to coil. It doesn't know what the spring is made of, if it's zinc or steel or brass or whatever. The masses only feel a force from this spring. So All of that is wrapped up in the spring constant, because remember the spring constant times the change in length of the spring from its relaxed length. So there it's relaxed. That is the only thing that affects the force is the distance and the spring constant. And the distance is, of course, not a function of the spring itself, not its manufacture, but how far it's been moved. So the spring constant. So we can affect the mass. We can affect the stretch of the spring from the equilibrium position is what we're going to call that stretch from the equilibrium position. So I'll throw it up on the screen here and then talk about it. So we can affect the mass, M, the initial stretch. I would like you to write initial stretch from the equilibrium position. Call that A, and the spring constant, which we could use K. We'll do K later. You're going to do one of these two, the mass or the initial stretch. And what I mean by initial stretch from the equilibrium position, well, equilibrium means things are balanced. In our class, equilibrium position is when the forces are balanced. So the spring force up equals the gravity force down. So this is the equilibrium position for this system. If I were to have just one mass, this would be the equilibrium position, which is a little different because a mass on a horizontal spring, the equilibrium position was when the spring was not squished or stretched. That's when the net force was zero if this were, horizontal. Okay, but if it's vertical, this is the equilibrium position. So we're going to measure our stretch from the equilibrium position. So if we pull this down 1 centimeter, right, and let go, we pull it down 1 centimeter from the equilibrium position. Some of you will be doing multiple masses. So when you hang a new mass on, the equilibrium position changes to down here, and then you will still pull down 1 centimeter from here. You'll use the ruler. So do something like this. I'd put the ruler down on the table here, and then figure out where that mass is, say the bottom of this one, pull it down 1 centimeter and let go, and then it will vibrate. Okay, I pulled it down more than 1 centimeter, but that's what we mean by the initial stretch. Okay, so how many things should we change at once when we do a lab? We can't change all 3 of these at once and figure out how they affect the period. We should change one thing at once. We'll do K later together, but we're going to change one of these. So some groups are going to be changing mass and leaving the stretch constant. And some of you will be leaving the mass constant and changing the stretch. Okay. So we want to change the independent variable by a factor of 5. So we're going to be changing either the mass for some groups by a factor of 5, and we'll go from 20 grams up to 100 grams, okay, by a factor of 5. So the group's changing mass. Let's do odd number groups. So you may not have a group 1 in your period. That's okay. But groups, 1, 2, 1, 3, 5, and 7 would be changing mass. And then groups 2, 4, 6 can change the amplitude, okay? So groups changing mass use constant amplitude of 1 centimeter. So these groups are going to start with, say, 20 grams on here. So again, use the ruler. I would use the bottom of the mass, make sure it's, not moving. Pull it down 1 centimeter. I'm not going to get a good 1 centimeter because I'm going fast here, but you're going to have to oscillate. And then later, you will put on 40 grams, measure 1 centimeter down for them, and then do 40, and then you do 60, 80, and 100. And we'll talk more. You'll do 2 trials each. So odd number groups are going to do that. Even number groups, you guys are going to change the amplitude. Yeah, I think you don't need to worry too much about this. I'm going to skip this since I'm not there with you. Measure delta L when 40 grams hangs. Don't worry about it. I'll do my own little lab here. We don't want the acceleration. We don't want the amplitude to be bigger than the delta L. So I'm going to tell you the answer to measure this. Measure delta L when 40 grams hangs. Well, actually, you can do it. So basically what I'm saying is everybody can do this, no matter whether you're changing mass or amplitude. So if I go like this and measure the length of the spring, the big deal for right now is my spring's about 14.6 centimeters. And then if I hang these on there, I'm gonna go to there again where the spring was. This is 40 grams on there. It's about 22.5, 22.6. So it's about 7.9 or 8 centimeters. So my point in doing that was, if you remember, we wanted to change the independent variable by a factor of 5. But if we went 2 centimeters, 4 centimeters, 6, 8, 10 centimeters, if I pull this down 10 centimeters and this spot is only 8 centimeters up, what happens if I pull this down 10 centimeters from here? If I pull it down 10 centimeters, it would go up 10 centimeters and try to go up another 10 centimeters. But when it goes up 10 centimeters, the spring would start to bend out of the way and the masses might come off. So we cannot stretch this more than 7.9-ish, 8 or so centimeters down. So if we're going to change our independent variable by a factor of 5 here, then we need to just do 1 to 5 centimeters, okay? So even number groups, you're going to keep the mass the same. You're going to keep 40 grams the whole time. So we'll control of 40 grams. So keep 2 masses on there the whole time. And you're going to have an amplitude of 1 centimeter to 5 centimeters. So that's going to be going like, kind of showed you this before, but whatever mass is hanging, let it hang first, then pull it down by 1 centimeter, okay, and let go. All right, you'll end up adding a total of 5 masses on there. 5 masses is going to get pretty close to the table at the bottom here, but I don't think it's going to hit the table. If it does hit the table, you can raise this up or even stick it over the edge, twist this around, loosen this, make this go over the edge of the table, and then it will not hit the table, okay? So everybody, to save some time, we're going to do 2 trials instead of 3. Do 2 trials, timing 10 periods. So kind of like when we did the circular motion lab, if you remember when we had that rubber stopper in the glass tube. Oop, dropped a mass. Rubber stopper on the glass tube. Okay, and we whirled it around. We counted 10. So rubber stopper, glass tube, we counted 10 oscillations of this thing when we were whirling it around. Okay, we counted 10 and then divided by 10. So we're going to do something similar to that. We're not going to do 3 trials, just 2 for the sake of time, but you're going to count like this. So it says do 2 trials of each, timing 10 periods. We'll have a measurer person, one person measuring the amplitude. So one person is going to, and then let go. The other person, a timer, you're going to have a timer and at least 1 recorder. If you have more than 3 people, you can have 2 recorders, 2 people writing down the numbers. So you're going to do something like this. You're going to, so amplitude people are always doing 1 centimeter, okay, and adding different masses. The mass people, the amplitude people are going to be using 40 grams and then changing the amplitude, going down 2 centimeters, going down 3 centimeters, going down 4 centimeters and 5 centimeters and letting go. Okay. And then the mass people will always be doing 1 centimeter down. Okay. And then 2 masses go from the equilibrium position 1 centimeter down. Okay. And timing 2 trials. All right. And when the person, so a person that's measuring the amplitude, they measure this and then they let go. And then the timer is going to do something like this. So I didn't pull down very well. So I'm kind of pretending here because I'm going fast about there. And the timer is going to go, oh, it doesn't look like it's oscillating up and down very well from your camera angle, does it? A little better. So go like this. Okay. 3, you're not saying 1, 2, 3, go and let it go. It's just 3, 2, 1, start. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop. Okay, so get the beat of it, time 10 oscillations, and then do another trial. If they're vastly different, figure out which one was wrong, do a third trial, okay, and throw one of them out. So at the end of that, what you are going to do is you are going to, our goal again is to figure out the factors affecting the period of a mass oscillating on a vertical spring. Okay, so you're going to get 10 times here. So on a piece of paper here that you've written factors affecting the mass, affecting the period of a mass oscillating on a vertical spring. Let's start or continue writing. So I'm going to go to paper here. Okay, so you're going to have one of two things over here. So don't do both. You're going to either have mass in grams, something like this, or if you're changing the mass, or amplitude. For now, you can leave it in centimeters. Okay, so if you're doing the grams, the mass, you're going to go 20.0 grams out to 100 grams. And then if your amplitude, you would do 1 centimeter to 1, 2, 3, 4, 5 centimeters. Okay, so just pick yours. Again, odd groups are doing mass, even groups doing amplitude. Then you're going to time the time for 10 periods. So that's the time for 10 periods, trial 1 in seconds. And then the time for 10 periods 2, that's going to be in seconds. And you're going to end up with 2 trials for either 5 masses or 5 amplitudes, so 10 total times. And then we are going to take the average. So just take these two numbers, add them up, divide by 2. And then we're going to find a period in seconds. We'll just take this number and divide by 10 to get the period. And that's just moving the decimal place over 1. So that should be pretty easy to calculate. So get these 10 values. So stop and work with your group. Get 2 trials for either 5 masses for odd number groups or 5 amplitudes for even number groups. Okay, if you've got data, here's some representative data. This is data from students. So you might have something like this. It might be similar for your times. And then we divide by 10 to get average times for the period. Okay, here is changing the mass, and here is changing the amplitude. Okay, so what I want you to do is I want you, when say an odd number or even number group close to you, so maybe it's going to be a little bit difficult because different periods have different numbers, but share your data quickly with if you're an even group, an odd group close by. If you're an odd group, an even group close by. Okay, so just take 2 minutes and look at their data, see what it looks like. Okay. Okay, if you come back here, this is data that's representative of the changing the amplitude. Okay, so look what happens when we change the amplitude. When we double the amplitude, like here to here, what happens to the period? Well, if you look at the graph, here is the graph, it looks like this. So what's the relationship? When we double the mass, what happens to the period? Nothing really. It stays constant. So what's the relationship between these two? The period is unaffected by the amplitude. It's unaffected by the initial stretch from the equilibrium position. The period pretty much just stays the same, perhaps shocking to you. So the period is not a function of the amplitude. Okay, so let's look at this. When the mass goes up, what happens to the period? We see as the mass goes up, the period goes up. So it's some sort of direct relationship. It's not an inverse relationship. Inverse, the mass would go up and the period would go down if they were inversely related. It's a direct relationship. But what happens if we double the mass, say? If we double the mass, does the period double? It does not. So what is the relationship between the period and the mass? Well, think about this. This number is nearly double that number, right? This is almost 0.8, and this is just above 0.4. And that would be taking the mass and quadrupling it, right? So we need the period to double when the mass quadruples. So let's think about what kind of relationship would give us the period doubling when the mass quadruples. So the period is not a function of the amplitude at all. No relation. How is the period a function of the mass? Well, is it proportional to the mass? We said no. If the mass doubles, the period does not double. If the mass quadruples, this doubles. So what kind of function would we do this? We want this to get bigger by 4, but this to get by a factor of 4, sorry. And this to only get bigger by a factor of 2. We need to square root the mass. Pretend to plug in 1, you get 1. Pretend to plug in 4, you get 2 over here, so the period would double. So the period is proportional to the square root of the mass. Let's give that a try in this data. So what I'm going to do is, I've already kind of done this. I cheated. I hid those columns. I square rooted the mass. Actually, this time what I want to do is, I think it would be better if I take this and I'm actually going to convert it into kilograms. So divide by 1,000. There. All right. And then this is the mass in square root kilograms. Square root mass in square root kilograms. Okay. So here is the graph of the original graph. Sorry. This is the period versus the mass. It was in grams. And it might look pretty linear. In fact, 0.987 seems like that's not such a bad R squared value. However, if you can see, it's kind of actually curving this way. Yeah. So if we make a graph of the, I think I need to remake the graph of the square root. Actually, this is the Y value. So the period versus the square root of the mass. Insert chart. We need a scatter. Oh, it gave me no x-axis. I want this on the x-axis and not at all that. Oh, that looks pretty good. Let's change the horizontal axis so that we can see the 0. I'm going to zoom out here in my whole thing because it's just hard to see. Okay. And then let's go to series, trend line, defaults to linear, equation, R squared value. Ooh, the R squared rounds up to 1. And our slope is 2.76. Let's get this out of the way. So it looks like the period is indeed proportional to the square root of the mass. I know I didn't change these. Excellent. I don't want to put controls in there at all. So we now know that it seems like the period is indeed proportional to the square root of the mass. Okay. Now, what about the K value? Well, if we were to take a look here at, if we were to take a look at this spring, if I were to attach another spring to it, imagine I take, actually, I'll go grab another spring here. Okay, I'm going to grab another spring. Now, if I were to go like this and pull this down, right, and attach it, we would get twice the force for the same stretch. So twice the force for the same stretch means K is doing what? Actually, or I could also do this. Go like that. Okay. Now they didn't stretch so much. So we have 2 forces equal mg. So each one of these is going to be holding half the weight. Okay. So let me go back to here. So I'm going to call this, pretend like my 2 springs over here are 1 spring. Okay. So if I solve for K, spring force over delta L, the spring force is staying the same. Both case, my two springs are still holding up the mass. So this is staying the same. And delta L is going down by a factor of 2. Okay, each spring is only holding half the weight. So each spring is only stretching half as much as it would if we're by itself. So my combined spring is only stretching half as much as one spring, and it's providing the same force. So my K value is essentially doubling. We're essentially taking the K value and doubling it. All right. So now what I'm going to do is I'm going to go like this, and we're going to do a quick little lab together with this. We already know the amplitude doesn't matter very much. So I'm going to time 10 oscillations for this spring. It's really 2 springs, but if you remember, we just made K double. All right. So we go like this, and I'll go 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I got 4.03 seconds. 4.03 seconds for my 2 springs. So K is doubled. And that was with 40 grams. And let's go and look at what the students got. Hopefully these springs are similar. Okay, so, oh, interesting. They got almost the exact same time over here with 20 grams. Okay, but so here's my 40 grams. Yeah. And they had 5.7. So when K went, what? We made 2 springs, K went up. So 1 spring, K, 40 grams was 5.70 seconds. So I'm going to go back here. When K doubles, we have less time. So this was 1K. This was the period. So when K goes up, the time goes down. So there must be some sort of inverse relationship, okay? So is it cut in half? When K doubles, the time gets cut in half? No, this is nowhere close to half. It's way more than half. Let's figure out what that might be, though. I could try it a different way, but I'm going to try it this way. I'm going to take the 5.70 and divide by 4.03. It gives us this number. Ooh, that's a very nice number. Very nice number. What number does that remind you of? When K doubles, when K doubles, the period gets not cut in half, but it goes down by this factor. That's how much it went down by. Okay, so it went down by √2. If you look at √2, it's very similar. Okay, so it turns out that when K goes up by √2, this goes down by √2. So this is, sorry, I said that wrong. When K doubles, the period goes down by √2. So we could try, so we could do more with this, but you're going to have to trust me if you didn't quite catch all of that. The period goes, when K gets bigger by 2, this goes down by √2. For instance, take 5.70 and divide by square root of 2. Okay, 4.03 seconds. So that's what I actually measured. I didn't even fake it. That numbers are really good. Okay, so we get the period is proportional to the root mass, but divided by root K, or the period is proportional to the square root of the quantity, the mass, over the spring constant. Now, there is actually a way, I don't think it's going to be all that. I think this is going to be enough. We're going to need to get a constant of proportionality and figure out what goes right here. There is actually a way we could do that. Okay, so we can't change M and K in once, but if you remember, I did create a graph of T as a function. So let's just throw some constant in here. This is a constant of proportionality there. So T is equal to C over root K. I kept K the constant. I'm sorry, the students did when they did their lab. So if you graph T versus root M, the slope should equal the constant of proportionality over root K. The slope is not too hard to find. I think the units are just fine. This was our 2.76. Okay, so the slope is 2.76. Let's see, the slope would be 2.76. The units were seconds on the vertical axis and square root of kilograms on the bottom. I'm pretty sure I had that square root of kilograms, right? I believe so. Okay, so this looks good. So the slope is equal to the constant over root K, is 2.76 seconds over kilograms. I need a value for K. If you remember a long time ago, I took this guy, I hung 40 grams on one spring, and I measured it was about 7.9 centimeters that it went down. So we could use that to find a value of K. So we know if the mass is hanging there, spring force up equals gravity force down. So K delta L equals mg. So this was K equals mg over delta L. So K was, the mass was 40 grams, 0.04 grams. So that's kilograms times 9.8 newtons per kilogram. Oh, this is kilograms, newtons per kilogram. The kilograms go away. Newtons over, let's see, meters was 7.9-ish centimeters. Okay. So I'm going to get a value here for K. So 0.04 times 9.8 divided by 0.079 gives me a K value of about 4.96. We'll do 4.962. 4.962 newtons per meter. And I'm going to plug this in here. We've got to square root it. Actually, we got to solve for C. C is equal to 2.76 seconds per kilogram times the square root of 4.962. 4.962. Newtons per meter. A newton is a kilogram times a meter per second squared. So newtons per meter. The meters are going to cancel out. I'm sorry. I forgot the square root right here. This is square root kilograms. Square root kilograms. Square root kilograms. Square root kilograms. They're going to cancel out. We're going to bring this on the inside. Seconds goes on the inside of seconds squared. And actually all of the units go away. And we get a unitless constant of proportionality of 2.76 times 4.962. It's not going to come out perfect. It hasn't come out perfect. But oops, I forgot to square root it. Okay, 2.76 times the square root of 4.962 gives us 6.15. So constant proportionality is 6.15-ish. But we will prove to you, actually, that constant of proportionality is, the constant is actually 2 pi. 2 pi would be 6.28. We did pretty good, 6.15. So the period is looking like it's something like this. The period is equal to, the constant is 2 pi times the square root of m over k. And we're getting that experimentally. I'm just saying that, yes, I'm telling you we're going to prove that this is 2 pi, even though we got 6.15. Okay, so that is our lab activity of figuring out the factors affecting the period of a mass on a spring. Okay, so hopefully you met with the groups. Yeah. All right, so that's the end of this activity, and then you'll watch the next video.